All right, so here we have another question. If I have an n by n matrix A, explain why the columns must span Rn when I know A is invertible. So A is invertible means that it must be row equivalent to In, and so that must mean that there is a pivot every row, and that means that A spans Rn. All right, here's another question here. If A is an n by n matrix and Ax equals 0 has only the trivial solution, then explain why I know that A is invertible. So if this has only the trivial solution, that means A has linearly independent columns, and that means there must be a pivot in every column. And since A is a square matrix, right, that must mean there is a pivot in every row. And what that means is that it's equivalent to In, the identity matrix, and that must mean it's invertible. All right. So now we get to this really large and important theorem, the invertible matrix theorem. So if I've got a square matrix, all are equivalent. So either all are true or all are false. So A is invertible. A is row equivalent to the identity matrix. A has n pivot positions, pivot rows and pivot columns, because it's square. Ax equals 0 has only the trivial solution. The columns of A are linearly independent. That means since I have a pivot in every column and it's square, I have a pivot every row, so that means that it's 1 to 1. Oh, sorry, the linearly independent columns means 1 to 1. And that means that there is going to be a solution for every B in Rn. That means the columns of A span Rn, and that linear transformation is onto. And so here they're just saying C and D work as the inverse. There's a matrix we can multiply on the left, there's a matrix we can multiply on the right, and what that matrix is A inverse. And that I know, this is a big thing, that A transpose is invertible, and I know the determinant is not 0. So those are all true or all false. All right, so let's go play with some. So let's figure out whether these matrices are invertible or not. So looking at these two here, I can see that if I multiply by negative 3/2 between these two columns, they're related to each other. So for part A, the columns are multiples of each other. So it means that they are linearly dependent columns. And if they're not linearly independent, that means it's not invertible. All right. This matrix for part B here, I see the 0 vector. The 0 vector as a column makes this 0 vector in the third column makes the columns of the matrix linearly dependent, so not invertible. All right, and this last one here, I see I have a row of zeros. So for part C, there is not a pivot in each row So it cannot span R3, so that means it's not invertible. All right, so let's look at what we have here. If I've got this transformation Rn to Rn, again, if it's invertible, it has to be square. And if that's the transformation with the matrix A, to do the inverse transformation is to multiply by A inverse. All right, so here's the transformation. And then they want me to show that this transformation is invertible and then find out what the transformation is for the inverse. All right, so first I'm going to find the matrix A from the transformation given. So I get 6, -8, 5, 7. That's the matrix A. So I'm going to find the inverse. So I have 1 divided by the determinant. So that's 42 plus 40. And remember how we do this. We take and switch this diagonal, and we take the negative of this diagonal. All right, so this gives me 1 over 82. And I'm not going to multiply this in. I'm just going to leave it like this. Okay, so find a formula for the inverse transformation. That would be this inverse matrix times x, where this is the inverse.